NASA launched the Voyager 2 spacecraft on August 20, 1977, with the goal of studying the extrasolar planets and interstellar space. It was launched as a part of the Voyager program 16 days before its twin Voyager 1, on a course that took longer to get the gas giants Jupiter and Saturn, but allowed for more contacts with the ice giants Uranus and Neptune. The only spacecraft to have visited either of the ice giant planets is Voyager 2. Voyager 2 was the fourth of 5 spacecraft to leave the solar system after achieving solar escape velocity. The primary objective of Voyager 2 is to travel the Jovian system in 1979, the Saturnian system in 1981, the Uranian system in 1986, and the Neptunian system in 1989, was successfully completed. The spacecraft is now engaged on its extended interstellar space mission. As of March 7, 2023, UTC. It has been in operation for 45 years, 6 months, and 14 days. As of February 8, 2023, it had traveled 133.22 AU, or 12.384 billion miles from Earth. On November 5, 2018, the probe entered interstellar space at a distance of 122 AU, or 11.3 billion miles, or 18.3 billion kilometers, about 1658 light-years from the Sun, and was traveling at a relative speed of 15.341 kilometers per second, or 34,320 miles per hour. Joining Voyager 1, which arrived at the interstellar medium in 2012, Voyager 2 has left the Sun's heliosphere and is now traveling through the interstellar medium, a region of space outside the solar system. The first direct measurements of the density and temperature of the interstellar plasma are now being made by Voyager 2. What is the history of both Voyager 2 and the whole Voyager program? You will get to know this and plenty more as we dive into the details of today's show. However, before getting started with the video officially, here's a quick reminder that you can subscribe for free and like the video so that we can boost the algorithm. Comments are most welcomed. Through the NASA Deep Space Network, Voyager 2 keeps in touch with the planet. For 8 months in 2020, the probe's outbound communication was shut off due to Deep Space Network maintenance. On November 2, 2020, communication was resumed after a series of commands were sent, carried out, and returned with a message confirming successful communication. Full communication with the probe was reestablished on February 12, 2021, following a significant antenna upgrade that took a year to complete. The DSS-43 communication antenna, which is in close proximity to Canberra, Australia, is entirely in charge of maintaining contact with the probe. It was predicted that the early years of the space era that a periodic alignment of the outer planets would take place in the late 1970s and allow one probe to go to Jupiter, Saturn, Uranus, and Neptune by utilizing the then new technology of gravity aids. NASA started working on a major project called the Grand Tour, which had 2 groups of 2 probes each, one of which visited Jupiter, Saturn, and Pluto, and the other of which traveled to Jupiter, Uranus, and Neptune. System redundancy would be built into the spacecraft architecture to guarantee survivability for the duration of the mission. In 1972, the mission's scope was reduced, and the Mariner Jupiter-Saturn probes, 2 spacecraft evolved from the Mariner program, took their place. The mission would only involve flybys of Jupiter and Saturn in order to reduce the overall lifetime program expenditures, while keeping the Grand Tour option available. The name was altered to Voyager as the show went on. Voyager 1's main objective was to investigate Jupiter, Saturn, and Titan, Saturn's moon. Voyager 2 was similarly intended to study Jupiter and Saturn, but its course would have allowed it to either divert to Titan as a backup for Voyager 1 or continue to Uranus and Neptune. Voyager 2 would receive a mission extension to send the probe towards Uranus and Neptune after Voyager 1's goals were successfully met. Spacecraft design. In order to keep the high-gain antenna pointed towards Earth, Voyager 2 was built by the Jet Propulsion Laboratory, JPL, and equipped with 16 hydrazine thrusters, 3-axis stabilization, gyroscopes, and celestial referencing instruments, Sun Sensor Canopus Star Tracker, the Attitude and Articulation Control Subsystem, AACS, which also includes 8 backup thrusters, and redundant units of the majority of the instruments, includes all of these instruments collectively. 11 scientific instruments were also built onto the spaceship so that they could observe and study astronomical objects as they passed by. Communications. Voyager 2 had a sizable 3.7-meter or 12-foot parabolic, high-gain antenna to transmit data via the Deep Space Network on Earth because it was designed with the intention of eventually traveling interstellar. As a result of the inverse square rule, communications are carried out over the S-band, with a wavelength of about 13 centimeters, and X-band with a wavelength of about 3.6 centimeters, offering data speeds as high as 115.2 kilobits per second at Jupiter's distance, and then steadily diminishing as distance increases. The digital tape recorder DTR can store around 64 megabytes of data for transmission at a later time, when the spacecraft is unable to interact with Earth. Power. 3 multi-100-watt radioisotope thermoelectric generators are installed on Voyager 2. MHW RTG. Upon launch, each RTG produced enough heat from its 24 compacted plutonium oxide spheres to provide about 157 watts of electrical power. At launch, the RTGs provide the spacecraft with 470 watts overall, halving every 87.7 years. They were expected to permit continued operations through at least 2020, and they already have. Attitude control and propulsion. The spacecraft included a propulsion module made of a 1,123 kilogram or 2,476 pound solid rocket motor and 8 hydrazine monopropellant rocket engines, 4 of which provided pitch and yaw attitude control and 4 of which controlled roll due to the energy needed to achieve a Jupiter trajectory boost with an 825 kilogram or 1,819 pound payload. The propulsion module was discarded immediately after the successful Jupiter burn. On the mission module, 16 hydrazine MR-103 thrusters regulate attitude. The remaining 4 are divided into 2 redundant 6-thruster branches that stabilize the spaceship on its 3 axes, while the 4 employed for trajectory correction maneuvers. At any one time, only 1 branch of the attitude control thrusters is required. Thrusters are supplied by a single 70 centimeter 28-inch diameter spherical titanium tank. It contained 100 kilograms or 220 pounds of hydrazine at launch, providing enough fuel until 2034. Launch and trajectory. On the August 20th, 1977, NASA launched the Voyager 2 probe from Cape Canaveral, Florida Space Launch Complex 41 using a Titan IIIe Centaur launch vehicle. On September 5th, 1977, the identical Voyager 1 probe was launched 2 weeks later. Though Voyager 2 had been launched on a longer, more circular orbit, Voyager 1 arrived at both Jupiter and Saturn earlier. Initially, Voyager 1's orbit had an APHE Lion of 8.9 AU, 830 million miles or 1.33880 million miles or 1.42 billion kilometers. The initial orbit of Voyager 2 fell very short of Saturn's orbit, with an aphelion of only 6.2 AU or 580 million miles, 930 million kilometers. Voyager 2 encountered a problem in April 1978 when no directives were sent to it for a while, prompting it to transfer from its primary radio receiver to its backup reception. The primary receiver eventually stopped working totally after that. The backup receiver was working, but due to a faulty capacitor, it could only pick up messages that were delivered at a specific frequency, and this frequency would be influenced by the Earth's rotation due to the Doppler effect and the temperature of the onboard receiver, among other factors. Engineers had to determine the precise frequency of the signal for each transmission to Voyager 2 so that it could be picked up by the spacecraft. Interstellar mission. After completing its planetary mission, Voyager 2 was said to be engaged in an interstellar mission that NASA is utilizing to learn more about the solar system's outermost regions. Approximately 160 bits per second of scientific data are being transmitted by Voyager 2 right now. Voyager weekly reports include details regarding the ongoing telemetry exchanges with Voyager 2. The Nova V1974 Cygni was seen by Voyager 2 in the far ultraviolet in 1992, and Jupiter in July 1994. Due to the craft's position, it had a clear line of sight to the hits, allowing for observations in the radio and UV spectra. Calculations revealed that the fireballs were just below the craft's limit of detection, yet Voyager 2 was unable to detect anything. On November 29, 2006, a telemetered command to Voyager 2 was randomly misinterpreted by the spacecraft's onboard computer as a command to switch on the magnetometer's electrical heaters. These heaters were left on until December 4, 2006, during which time the temperature rose above 130 degrees Celsius or 266 degrees Fahrenheit, much higher than the magnetometers could withstand. And one sensor rotated 180 degrees from its intended direction. Although efforts were being made, as of this date, it had not been possible to thoroughly diagnose and repair the harm done to Voyager 2's magnetometer. Voyager 2 crossed the heliosheath on August 30, 2007, passing the termination shock and coming in at a distance from the Sun of around 1 billion miles or 1.6 billion kilometers. Deep space's interstellar magnetic field is to blame for this. The heliosphere of the solar system is being pulled towards the south. Voyager 2 ran into issues with the format of scientific data on April 22, 2010. JPL engineers identified the issue as being caused by a flipped bit in an onboard computer. on May 17, 2010, and scheduled a bit reset for May 19th. As engineers repaired the flipped bit, Voyager 2 started sending science data once more on May 23, 2010. The idea of blocking access to or prohibiting use of the memory location with the flipped bit is currently being researched. The low-energy charged particle instrument is currently in use, and information on charged particles is being sent from this device to Earth. The information enables measurements of the termination shock and heliosheath. The onboard flight software has also been changed to delay shutting off the AP Branch 2 backup heater for a year. The explosion was planned for February 2, 2011. Voyager 2 was in the constellation Telescopium, as seen from the Earth on July 25, 2012, when it was moving at a speed of 15.447 kilometers per second, or 34,550 miles per hour, in relation to the Sun at a distance of 99.13 AU, or 14.830 billion kilometers, 9.215 billion miles from the Sun. It was also at a position of 55.29 degrees declination and 19.888 h right ascension. This puts it deep into the scattered disk and gives it an outward motion of 3.264 AU, or 303.4 million miles, 488.3 million kilometers per year. It is significantly further from the Sun than Pluto and well past 9377 Sedna's perihelion. But it's still inside Eris's orbit's farthest reaches. Voyager 2 was 99.077 AU, 14.8217 billion kilometers, or 9.2098 billion miles from Earth, and 99.504 AU, 14.8856 billion kilometers, or 9.2495 billion miles from the Sun on September 9, 2012. It was moving at a relative speed of 15.436 kilometers per second, or 34,530 miles per hour, and was expanding outward at a rate of about 3.256 AU, or 302.7 million miles, 487.1 million kilometers per year. It takes 13.73 hours of sunlight to reach Voyager 2. The Sun seems magnitude 16.7 brilliant from the spacecraft. The Telescopium constellation is where Voyager 2 is headed. Uncertain. Discuss, in contrast, Proxima Centauri. The star that is nearest to the Sun is about 2.65 times 105 AU away, or roughly 4.2 light-years away. Voyager 2 is currently moving away from the Sun at a relative speed of 15.436 kilometers per second, or 55,570 kilometers per hour, or 34,530 miles per hour. This is about 10% slower than Voyager 1 and equals 3.254 AU, or 302.5 million miles, 486.8 million kilometers each year. If Voyager 2 were moving in the direction of the nearest star, Proxima Centauri, it would take 81,438 years to arrive there at present speed. At its current speed, Voyager 2 will take approximately 19,390 years to travel one full light year. Voyager 2 became the second spacecraft built by humans to reach 100 AU, 9.3 billion miles, 15 billion kilometers from the Sun on November 7, 2012, and it was the third to do so while continuing to transmit data to Earth. Voyager 1 was 122 AU, 11.3 billion miles, 18.3 billion kilometers from the Sun, and Pioneer 10 is presumed to be at 107 AU, 9.9 billion miles, 16 billion kilometers. While Pioneer has ceased communications, both the Voyager spacecraft are performing well and are still communicating. In 2013, Voyager 1 was escaping the solar system at a speed of about 3.6 AU, 330 million miles, 540 million kilometers per year, while Voyager 2 was escaping at 3.3 AU, 310 million miles, 490 million kilometers per year. Voyager 2 was 120 AU, 18 billion kilometers, 11.2 billion miles from the Sun on February 25, 2019. The Earth's rotation around the Sun in relation to Voyager 2 results in variations in the distance from Earth. The plasma spectrometer on Voyager 2 was supposed to make the first direct measurements of the density and temperature of the interstellar plasma when it entered interstellar space in early 2016. Voyager 2 entered interstellar space on November 5, 2018, according to an announcement made by project scientist Edward C. Stone in December of the same year. Interstellar space discoveries by Voyager 2. The probe saw some noteworthy variations in the sibling Voyager 1 as it traveled beyond the solar wind's bubble. A year ago, the Voyager 2 spacecraft exploded out of the bubble of gases that was created by the Sun into the Milky Way's untamed interior. The second spacecraft to cross that line and make direct observations of the interstellar medium was this one. Voyager 1, its faster-moving twin, completed the crossing in August 2012, 6 years earlier. The twin spacecraft, which were launched 42 years ago, during Jimmy Carter's presidency, has endured far longer than anticipated, as is their capacity to return scientific discoveries to Earth. The observations made by Voyager 2 at the outer edge of the solar wind bubble and beyond are detailed in a series of papers that were published on Monday in Nature Astronomy. The mission's project scientist Edward C. Stone expressed amazement about the probe's endurance at a news briefing on Thursday. We're also quite thrilled that they do too. The space age was just 20 years old when the two Voyagers were launched. At the time, it was difficult to imagine something lasting more than 40 years. The data were similar to those made by Voyager 1 in many ways, including a change in magnetic fields and a surge in particle density that was accompanied by a rapid drop in particle speed. These changes were also detected by Voyager 2, which may provide information about the complex dynamics in that part of the solar system. The solar wind, which travels at a speed of 1 million miles per hour, is a constant stream of particles that the sun continuously ejects in all directions. Most of the particles are hydrogen, but when heated to a temperature of around 3 million degrees Fahrenheit, the hydrogen atoms are split into protons and electrons. The solar wind, which is thinning out at a distance of more than 11 billion miles from the sun, is being progressively buffeted by the flow of particles in the interstellar wind and a galactic magnetic field created by the explosions of far-off stars in the distant past. The temperature of the interstellar wind is simply tens of thousands of degrees, and it is also much denser. Some of the disparities could be explained by the fact that Voyager 2 is traveling in a different direction than Voyager 1. In 2012, which is also close to the peak of its activity cycle, the sun was likewise more active. The solar minimum, a period of low solar activity, is about to arrive. With Voyager 1, the solar wind was pushed sideways, and its outward velocity was zero well before the boundary. The outward velocities of Voyager 2 fluctuated, occasionally falling to zero and then climbing again. Strangely, the separations from the sun for the two exits from the solar system were comparable. The bubble is supposed to expand during the solar maximum and contract during the solar minimum, according to scientists' predictions. A lot of the models left a lot to be desired, said Stamatios Karmigis, a physicist at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, and the lead researcher on one of the Voyager instruments in an interview. A scientist working with the magnetometer on Voyager 2 described the measurement of the magnetic barrier like the pileup of slowly moving cars on a major highway, a few miles ahead of the scene of an accident. Leonard F. Pergala. The density of the particles rises as the solar wind slows and the magnetic field becomes more powerful, Dr. Balaga continued. Again, it's like the cars which divert away from the accident-prone lanes and proceed slowly down the open lanes. The drivers are hotter and the cars are more closely spaced, but soon they go on. The missions were initially intended to fly by Jupiter and Saturn for 4 years. Neptune and Uranus were also visited by Voyager 2. Voyager 2 still has 5 instruments that can be used to measure the emptiness, compared to Voyager 1 has 4. That brings our space trip for today to a close. What more might we ask of missionaries who have already left their posts? Do let us know your opinion on the comment section below. If you enjoyed this video, please hit that thumbs up. It will help us to understand our audience and allows YouTube to suggest similar videos to you. Thanks for watching, and we hope to see you at the next one.